Welcome to Advanced Reverse Engineering. There's homework. The homework is to compute the Hamming distance between two arbitrary numbers. So there you go. Here's a test harness you can use. I'm going to try a lot of different numbers. You can use any test harness you like. So you could modify that main program, perhaps, to read stuff from the command line. Yeah, why not? This is just a way for you to test it. All I want is your hamming.asm, and I will then test it. Here's the template for it. Let's talk about some tools. And let's talk about some tools like GDB, which so far I've been unable to get time to produce a video about. GDB is the GNU debugger. You'll probably need it as you start to write assembly. You'll want to be able to debug your assembly code, and one way to do that is to use GDB. In fact, that's pretty much the only way to do it. It's hard to put printfs in your assembly, but not impossible, just hard. So run will execute your program, just like it would if it were a C program. Typically in C, you would use start, which would start the program and go to the first statement. For a program that's a binary, it's an assembly, you'll want to use start I. That stops at the first instruction, usually at _start. Now, instead of going line by line through my program, I want to go instruction by instruction through my program. For that, I would use step I, step instruction, which I can abbreviate SI. Or I can use next I, which I can abbreviate NI. The difference is whether or not I step through function calls. So next I will step over function calls. Right? It'll execute the function call, but not go through it step by step. Step I will then step into the function call. Const continues your program from the current point and just resumes running it. Until is a super useful instruction. If I'm sitting at the bottom branch for a loop, I can say until, and the program will run until that branch is not taken, which lets me, immediately, if I got a giant long loop, I don't go through all of the iterations of the loop. I can say until and go to immediately execute the rest of the loop and then be at the bottom, ready for the next instruction. You can set breakpoints. B sets a breakpoint. We have to use locations because we're in assembly as opposed to line numbers or line locations in C. We use a location. We just say B and the location. Now, if you say B main or B print hex or B hamming, it will say, I know what that is. That's the name of a function. I'm going to try to interpret that and set the breakpoint where I think it should be for a higher level language. And that's probably not what you want. You probably mean for the breakpoint to be at the specific location that you're giving it. To do that, put an asterisk in front of the symbol. That's it, right? That breaks the notion that that the assembler knows what main or hamming means and says, oh, you want the location, and it puts it at that location. If you want to list the breakpoints that you've got, you can list them with info B, which you can abbreviate as just IB. By the way, location can just be an address. So I could say, set a breakpoint at this particular address. It could be a combination of a symbol and an offset. So set a breakpoint at main plus 20. All those things will work just fine. I can delete a breakpoint by giving D and the breakpoint number. What's the breakpoint number? I find that out by using info breakpoint, so info B. That will give me the numbers, and then to delete whatever, I just say D and the number. Likewise, I can enable and disable breakpoints with enable and disable and the breakpoint number. Finally, I can include conditions in it. So maybe I'd like to break at a certain location, but only when RCX is 0. I can do that by giving it the breakpoint I want and then saying $RCX equals 0. $RCX, by the way, is how I refer to registers. So $RAX is RAX, $RCX is RCX, $AX is the first 16 bits of RAX, etc. I can print an expression with print, which I can abbreviate as just P. I might want to print it in hexadecimal because I'm doing assembly stuff. P space / X will do that. What if I want to look at memory? That's X for examine memory. I give it a location and it tells me what's at memory at that location. X with a location tries to be clever and interpret the memory contents for me in a way that makes sense. I don't always want that, so I can be more explicit. So I can use the /, give it a number of things to show me, give it a size, and give it a way of showing it to me. So for example, 16xb says, show me the 16 bytes at the location I've given in hex. Okay, so the X is for hex, the B is for byte. What are the other sizes? Well, they're H for half word, which is a word to us, it's 16 bits. W for word, which is a double word to us, it's 32 bits. And G for giant, which is a quad word to us, or 64 bits. Just have to remember that they have the weird letters. If I do something like P/X RIP, I'll print the current instruction pointer value in hexadecimal. If I do something like X/3I RIP, I'm doing something a little different. Here, the I tells me I want to interpret what's at that location as an instruction. And this will print the next, this will disassemble and print the next 3 instructions at the address pointed to by RIP. I can reference RIP within the debugger. I can get it by using $RIP, and I can even set it by saying set RIP equal to some value. And I can do that for any register. If you want to know what's in all the registers, you can say info registers or I registers, and it will print them out. It'll print out the most common ones. For the other ones, there is an I all - registers that will print out more registers. It's not necessarily all of them, it's more. There's something called the terminal user interface, which you can get into with Control-XA and get out of with Control-XA. It lets you toggle between it. Let's go take a look at that real quick. So over here we are at the prompt, and let's go ahead and be sure we're in a profile that is the right one. Let's make things a little bigger. There we go. And let's go ahead and see what's in this folder. So there we go. Let's go ahead and build this. Oops, need max.o first. Okay, let's make, and then we'll try making that. There we go. Now we have a little piece of code, which we'll see a little later on, called max test. Let's go ahead and gdb max_test. So that will start the GNU debugger, and we'll come in here at this prompt, and I'll say no, I don't want to download debugging info for this session. I could just hit enter and the default would be no. That would work just as well. And now I'm ready to debug max test. If I forgot to specify that when I entered the debugger, I could get it by saying file max test. And there we go, and now I'm ready. I didn't mention this, but disassemble can be abbreviated disas, and I can give it a location. If I can type main, and this will disassemble the code starting at main, and it tries to show me the entire function, and you can see, in fact, it's done a pretty good job of that. It's run through here all the way up to the return, and then the pager stopped it, and I'm done. And it does a pretty job of showing it this way. If I put a /r in here, it will also show me the raw bytes that make up each instruction. And so that's another thing I can see with this. All right, so I mentioned the text user interface, and I said Control-X-A. Now I'm in the text user interface. Great. It shows me that there's no source available. That's because I don't have a source code file. I have assembly. I'd like to see disassembly. To get there, I could say layout ASM. When I do that, I switch to the assembly layout, and you can see, sure enough, I'm seeing my code at main. Now let's put a breakpoint in here. So I'm going to say, if I say break main, I've already told you it's going to try to be clever and put it at the right place. And you can see what it does is not put a breakpoint at main, but put it here at main plus 8. I don't want that. What I really want is a breakpoint up there at the top. So let's delete that. Whoops. There we go. D1, not B1, but D1 for delete. And let's put a breakpoint at star main or asterisk main. And when I do that, you see I get the breakpoint up where I want it. And just to be sure we remember this, I can disable that breakpoint with disable 2, right? Because it said that was breakpoint 2. Disable 2 changes a little plus you see up there into a minus, indicating the breakpoint is disabled. And enable 2 changes it back to a plus. Now, these are little windows that I see here. Oh, by the way, let me do an info breakpoint just so you can see what that looks like. That looks like this. It gives me an address, 1149. Sure enough, that's 1149. And I did mention you could use an expression like main plus 94. Yeah, if I can type. 94. And you see that's right here. What happens when I do that? Well, it's going to complain. So what do I need to do to make that work? Well, you remember I said B star main plus 94. And when I do it that way, sure enough, I get just what I want, which is a breakpoint at that location. And now IB shows me both breakpoints, and I can delete that breakpoint 3 because I really don't want it. Now, what if I try to go backward and forward through my command history? Oh, it doesn't work. I'm scrolling in this other window up here. Well, that's because that window has the focus. If I do info and windows, it will list the different windows. And you see I have 3. I have ASM, which is this top one. I have command, which is this bottom one. And I have status, which is this funny little thing in the middle here. It's a single line. Okay, it tells me the number of lines in each one. And it tells me that ASM has the focus. So if I say focus CMD, notice that immediately the display changed. And now if I do IWin, I find out the command has focus and my arrow keys work the way I want them to. I can also do Control X O to swap the focus back and forth between the windows that can get it. This little status line can't get the focus. So what if the focus is up there, but I really want to go back? Well, I can use Control P and Control N. So something to remember, Control P for previous, Control N for next. Let me scroll through my history even when I don't have the focus. Another thing is sometimes this window will get messed up because it's just a text thing. Control L will refresh the whole thing and redraw it. Great. So that's the text user interface. Again, layout, ASM will put you in it. In addition, I mentioned info on registers. If you try that before the program starts, it'll say there aren't any. Why is that? It's because there really aren't any, right? I mean, what does RIP mean in this situation? The program's not running. RIP isn't pointing anywhere, right? The process doesn't exist. So registers have no meaning. If I do a run, let's say, I'm going to break up at main, and now I've broken at main. You can see that this line is highlighted. At this point, things have meaning. So if I say info registers, then I get a list of the registers. And you can see here they are, and their current value is here, and the interpretation is over here. And sometimes this will be the decimal value for some. It will be a hexadecimal value for others where it thinks that makes sense. For things like E flags, it'll actually try to decode that into showing me which flags are set. Parity 0 and interrupt are set in this case. And so on. It tries to do the right thing. For RIP, that's a register. It shows me the hex address, and then it shows me also that it's main. Great. And of course I can print /x, $RAX, and see what that is as well. Now, I mentioned NI will move you to the next instruction, and so will SI, the difference being whether or not they go into subroutines. Maybe I'd like to be able to watch the registers the whole time this is going on. To do that, I can also say layout regs. If I do that, then I have this. Now it says registers unavailable. That's because I hadn't been displaying it, but as soon as I take a step, it's going to fill them in. And there they are. And again, if I do iWin, now I'll see I have an additional window, regs, and my little focus shifting can move between all those. And in fact, I can scroll up here in the registers to see other registers that might not be on top. So I can see what's in RAX. The very next thing I'm going to do is subtract 50 from RSP. So let's find RSP up here. Where is it? It's right there. I'm going to take 50 away from that, hex 50. So I expect that to be 0, 0 on the end. Let's go ahead and do a next I, NI. And you'll see that sure enough, it did in fact subtract. And this line got highlighted to indicate that this register was modified by the most recently executed instruction. What else was modified? RIP, which of course advanced to the next location. And E flags, right? I did a subtract, and so it set some flags. So this will tell me which registers were modified as I walk through this, right? And so here, for these instructions, I'm not modifying registers. I'm putting stuff in memory, but I am modifying the instruction pointer, so it's being shown. And then finally, I'm going to put something in RAX. Boom, it gets highlighted. Notice I'm just pressing enter. If I do an SI and I push enter and then I push enter again, it repeats the previous command. And that's convenient for just walking through stuff. All right, quit. Will quit me out of this. And I'm back at the prompt. So that tells you a lot about the text user interface. List the windows, focus, add the assembly layout, the register layout on top of that, and then move back and forth with the prompt. So, for fun, let's try another tool we haven't looked at. Let's try ChatGPT. Just another tool that's out there. And let's see what ChatGPT makes of your first homework. Your first homework was to take this hex dump and do something with it. So here we go. I tell ChatGPT, the following is a hex dump of an executable program for x86 Linux. Can you tell me what it does? Now, ChatGPT is a large language module, large language model. It's going to try to predict the next word, and that's basically all it's going to do. So what's it going to make of this? So put in your mind what you think is going to happen, and let's see what actually happens. ChatGPT replies, the provided hex dump represents the header and a portion of the beginning of a Linux 86 ELF executable linkable format binary. Let's analyze it step by step. There's an ELF header, and it pulls apart the pieces of that, and there's some sections, and it pulls apart those, and then it says, hey, there's some ASCII text in here, and then it says, based on the analysis, this binary appears to be a simple x86 Linux executable that prints the text, I am binary, followed by a new line when executed. It includes an ELF header, section headers, program headers, and actual machine code instructions for the program. Now, if this result surprised you, it surprised me too. I was quite interested in this and found that just absolutely fascinating. So, by all means, see what ChatGPT makes of stuff as we go along. I find it just fascinating. Let's look at a longer example. So here's a very simple program. Given a list of unsigned integers, find the largest one in the list. Doing it in C is pretty simple. So what are we doing up here? Hopefully the C code looks blindingly obvious to you. You can tell because it uses int a lot that I didn't really write this. I stole this out of a textbook to find the max of a list of integers, and there you go. So I'm given an array of values and a count, the number of things that are in that array. And I set my maximum to 0. They're all unsigned, so the lowest they could ever be is 0. And then my index runs from 0 up to, but not including, count. And each time I increment the index. So I go ahead and say, is the value in the array at position given by index greater than max? And if it is, that's my new maximum. And then when I'm done, I return the maximum. Super easy, simple stuff. Okay, we're going to build some code that does the same thing. Here is our initial pass at that code. We're going to call our function max. We're going to have the preamble where we push RBP and move RSP into RBP. And we're going to have the closing out stuff where I restore the stack pointer and then I pop RBP. Has to be in the opposite order, right? For lots of reasons, right? The original RBP has to be saved. And then I put the stack pointer in. So I can't do it in the opposite order down here, right? I've got to put that back in the stack pointer. Then I can pop RBP. And then the body will go in here. Here is this section note at the bottom, which is needed to avoid a warning. What's that warning about? It's about stack hardening. So are you all familiar with the basic security principle W caret X? What is that? That is the caret's the exclusive OR. This is things should be writable or executable, but not both. Remember, exclusive OR works when one thing is true or the other thing is true, but not when both are true, right? So we can be either writable or executable, but never both writable and executable. That provides too much room for mischief by bad guys. And so we don't want to let a attacker take control of executable memory. So if the stack is executable, we're in trouble because the stack has to be writable. So if it's also executable, that violates this basic security principle. Can an attacker use that? Maybe. But it's a basic principle and it's a good principle that we should follow. So how do we do that? Well, in some cases, the stack has to be executable. There are some compilers that use the stack for trampolines, for these special code that you jump to that would cause a jump somewhere else. That's becoming less common because we're really restricting what can be executable. But the way we're going to get it is by including this note in our program, usually at the bottom. The first thing we're going to do is declare a section. This is going to be the section name, and it's basically just a little marker that we're putting in to indicate to the rest of the stuff that comes after it that we want the stack to be not executable. We're not going to allocate any space. Nothing's going to be in our section. It's not going to be executable. We're not going to write anything to it. And this is just the default. Proc-bits is the default. You can omit that and it would be assumed. So we are typically not going to write all this stuff. When we write this statement in our program, we're typically going to abbreviate it to just section and no exec. We really don't even have to say that. We can just say section with the name, but no exec sort of is nice to have in there to indicate what we're doing. So there it is at the bottom, section, note, GNU stack, no exec. Just include that at the bottom and you're fine. If you include it at the top, you have the risk that you didn't actually specify section text. In this case, I didn't. And suddenly all this is in the GNU stack section. I don't want it to be there. So let's put it at the bottom where nothing else can get into it. All right. So we're going to need a scratch register to hold our maximum value. Now, our values are going to be 32 bits. So we might as well use the 32-bit view of a register. In this case, we'll use EAX to hold the max. And that's convenient because EAX is not one of the ones we get an argument in, but it is where we store the return value. So if we just want to use EAX, we're fine. We're free to override it. It's not a register that the caller expects us to preserve, obviously, because it's going to hold the return value. So that's great. That's a good choice for our max, which is what we're going to return anyway. It's like setting a return value variable, and then at the end we just return the return value. Okay. So that will hold our max, and we're just going to use the 32-bit. So we'll put 0 in there as our initial max. Now we need a loop. And so we're going to have .loop, and then we're going to do something down at the bottom with this. So what are we doing here? Well, some stuff's going on. Let's go back and let's recap what everything is. When our function is called, according to the calling convention, we're going to get a 32-bit argument that will hold the array length. So the first argument comes to us in RDI. But we only care about the low 32 bits of it because, right, we're getting an unsigned int, which is 32 bits. So really it's coming to us in EDI. You can think of it that way. The array pointer is a pointer. Pointers are always 64 bits. So that comes to us in the second argument, which is RSI. Return value goes in EAX, and we're going to use ECX as our loop index. So initially we set that to 0, just like we did in the for loop. Every time through the for loop, we're going to compare the index to 64, and if we haven't hit 64 yet, then we'll go and jump back to the top. So what about that? Well, I said 64. Why did I say 64? Ignore what I just said. We're going to compare the index to the number of things we got, the count. And as long as we are below the count, we're going to continue the loop. Sorry about that. So we'll set our index to 0. At the bottom of the loop, we'll compare our index to the count, which came to us in EDI. If we are below, right, if ECX is below EDI, then we'll go back up here to the loop. That's a jump below. And below is the right one. Less than we would use for signed. Below we use for unsigned. Okay. So that will take us back up here. We'll do the loop again. Every time through we increment ECX, compare it, and then jump if we've not reached the end. And when we're done, we don't have to do anything else because our RAX already holds our return value and we're fine. So now we need a few more things. What if, let's go back to this, what if we come in and the array is empty? That's a possible thing, right? That could happen. If we come in and the array is empty, we don't want to run the loop body. There's a couple different ways to handle that. We could move the check up to the top. Sometimes that's done. And if the check fails, we jump to the end. We saw that in a previous example. But in this one, we'll do something a little different. We'll look for that specific case. So I will compare EDI to 0. And if they're equal, if EDI is equal to 0, I will jump to .out, which will take me down here. And then I'll exit. Will that return the right value? Yes. I've already set EX to 0, so that will return 0. Otherwise, I fall into the loop. Now I can move this ECX expression down below this, right? But I really don't care. Okay. Now, what's going to have to happen in here? Well, in here, we're going to have to do this comparison to see if the array entry at the index is greater than max. Well, we know the array pointer is RSI, and we know the array index is ECX. So what we're going to do is we're going to take RSI, we're going to add RCX times 4. Why RCX? Because again, we have to use 64-bit values inside the brackets. We have to use things that are 64 bits long. We just have to. And that's okay, because we set ECX to 0, which automatically 0 extended into RCX. So RCX was initially 0. Each time we increment it, right, we're setting those top 32 bits to 0. Every time. So we'll go here, we'll get the D word at this location, and we'll compare it to EAX. And if that is greater, we need to set EX to that value. So let's populate that code. This is what it looks like. So I will compare EAX to what's in the array at the position given by RCX. The times 4 is because each entry is 4 bytes long. It's an unsigned int. If I am above or equal, if EAX is above or equal to this, I jump to skip right here. Otherwise, I take this value and I put it in EAX. Okay? I could invert that test. I could reverse these two, and I could use below equal, right? Doesn't matter that much. I just like how these look nicely the same. Okay, this kind of jump over logic is super common. Super common. Okay. So here's our complete program. This is the complete code for our function to find the max of an array. We're given the array length and an array pointer, and we find the largest 4-byte unsigned int in that array. Notice our make line only assembles it. That's because we don't have a main function in here. We have to link this with something else that will then call it. We never use the section directive, but we could. We could say section text up here at the top, and we probably should. So, there's other stuff we can do, but let's not worry about that for right now. Calling it from C, how do we link this up with our C program? Well, we create .c files and compile them with -c, right? Just like you normally would. Inside those, we use extern, or we use an implicit extern to declare our assembly resources that we need. We can have variables in our assembly program and reference them using extern. We make them global, and then we'd reference them with an extern. I can have a data element in my assembly. I declare it global up at the top, and then I can extern it from my C program and reference its content. Really, you can do that. So I can do that to get any resources I need. And if I just give a function prototype, that is implicitly extern. The system will expect to find that somewhere else. Understand where arguments and return values go, as per the calling convention. Then I create assembly files and assemble them. I use extern to declare any C or other assembly resources I need. I set up the arguments and call the function according to the calling convention. I make sure any symbols I want to export are declared global. And then ultimately I just link everything with LD or with GCC, depending upon whether I want the C runtime to be included. And if I'm linking with C, I almost certainly do. I'll have to, so I'll use GCC in that case to link everything together. Linking is a bit obscure. If you want the C runtime, you should let GCC build the program for you. So here I have an explicit line. GCC, I use -static. So for right now, until we learn how dynamic linking works, you would use -static. M64, our program will be called hello, greet.o and hello.o. I link all those together. Don't care where they came from, and I build a program. Down here, I can do the same thing with LD, but I have to include parts of the C runtime. CRT is the C runtime, and it has several different little pieces that have to be linked, or should be linked in order, and the C standard library that needs to be linked in. All right. If you're curious about what GCC does for a particular program, run it with -v and be prepared for a lot of output. Linking is tricky. So here's a test program to test our little thing. I have a big long line up here at the top. You don't need to worry too much about it. It's kind of fancy. It checks to see if max O exists, and if it does GCC stuff. If it doesn't exist, it says I need it. And we saw that a little earlier. I wanted to explicitly do that so you could see how that worked. Then I import standard I/O. Here's the prototype for my max function, which implicitly says this is an extern thing. Here's my main function. I create a list of values right here. I compute the length of it like this. This works. I take the size of the whole values thing. I divide it by the size of one of them. That tells me how many there are. I pass values, and then I'm done. And I print out the result of that and return 0. This code does not care how max is implemented. It could be C, it could be anything, right? As long as it can call it using the standard calling convention, and it can find it and link with it. So we make max.c, then we make max_test.c, then we run it and we get 103. This used our original C implementation of the max function. What about our assembly implementation? So instead, we do make max.asm, then we do make max.test.c, which links with whatever max.o is. In this case, it came from assembly. We run it and we get the same value. Yay, our assembly code works. Let's think of some improvements we can make in our code. We never use the stack. We never refer to anything on the stack. We have no reason to do the stack stuff, right? I mean, we just don't. We never do anything with it. So let's get rid of it. If we called another function from inside here, we could probably still also get rid of it because that function would be responsible for keeping up with the stack stuff. So a lot of times you'll see this stuff being omitted, especially when you optimize a program. Like when we optimized that last one and it threw everything away except for the one move instruction. Okay, so we don't need that stuff. It will be, we can just throw it away. So now our program looks like this. Well, there are some assembly idioms we can use. Instead of putting 0 in a register, we can exclusive OR the register with itself. Does that work? Well, yeah, because everywhere there's a 1, you get 1 XOR 1, which is 0. Everywhere there's a 0, you get 0 XOR 0, which is 0. The whole thing goes to 0. So in fact, that's the idiomatic way to do it. Exclusive OR EX with itself and ECX with itself. So when you see those, you'll know I'm setting that register to 0. Okay? Comparing something with 0, we don't do that either. Instead, we do test RDI RDI. We talked about test before. It ANDs a register with some other value. In this case, the register with itself. When is that result going to be 0? If the register is 0 and never any other time. So a way to test if something is 0 is to AND it with itself and see if the result is 0. Test does that without saving the result. It just sets flags. So a quick test to see if EDI is 0 is to do test EDI EDI, and then we jump if equal out. Well, that should really be jump if 0 out, but remember, those are synonyms. JE and JZ are synonyms. So we're going to jump to out exactly when EDI is 0. So it's gotten much simpler. And let's take a quick look at what we did. So here's the compare instruction. We're going to compare RDI with a strict 0. We said strict, which says, I really mean it. Go make me an 8-byte 0. The assembler says, I hear you, and I see that strict you put there, and I know you really mean it, so here's your 4-byte 0. Right? It ignores strict in this case and gives this to us. Why? Because it turns out there is no version of compare that works that way. Interesting, huh? So here's a compare of RDI and 0. By default, it's going to give us this, which is shorter. What about test RDI with itself? It's even shorter. What that means is we can fill more pipelines, more things can run in parallel, the whole thing can run faster. How about moving a strict 0 into RAX? Yeah, it will do that. It will give us an 8-byte RAX and put it in, or 8-byte 0 and put it in RAX. If we just do that with using the 0 extend, much simpler. What about exclusive ORing RAX with itself? That gives us a 3-byte version. What about XORing EAX with itself? Well, that's going to automatically 0 extend into RAX, so it's exactly the same as the instruction above. Is going to have the same effect of putting 0 in there, and it's just 2 bytes. So that's what we're going to want to use. All right, let's talk about C objects versus assembly. So let's disassemble our code, and what we'll get back is what you see over here on the right-hand side. And, you know, our program uses 23 bytes, right? We go up to, we start at 0, and we go up to address 16. That's 116 plus 6, which is 22. And since we started at 0, it's really 23 bytes long. So there we go, 23 bytes. Let's go ahead and compile the little C code we had earlier and see how that fares. Well, that is what we get out from compiling our little C function. It goes from 0 up to 2A. 2 times 16 is 32, plus 10 is 42, plus one more byte because we started at 0 is 43. 43 bytes. So already it's longer. How does it work, right? We still have the same things. It's still going to find the array length in EDI and the array pointer in RSI. The return value will still be in EAX. So the first thing we're going to do is check to see if EDI is 0. Is the array length we're given 0? And if it is, it's going to branch down here to 28, which zeroes out the return value and then returns. Simple stuff. It's going to check that special case as the first thing. Then it does this. What is this? What is move EDI EDI? So think about this for a few moments and try to answer the question, does this actually do anything at all? Right? Does putting EDI in EDI have any effect? Well, it actually does. This actually zeroes out the top 32 bits of RDI because of zero extension. So, you know, who knows why this is in there? Maybe it's in there as a defensive thing, but it basically means that now we really do have a 32-bit value with nothing in those top 32 bits. Is this necessary? Is it a good idea? It's probably a good idea, but is it necessary? Who knows? The next thing it does is it zeroes out EAX. It's going to do the same thing we did and store the max value in EAX. The next thing, it goes ahead and loads an address into RCX. What address does it load? Well, RSI is the start of our array. RDI holds the number of things in the array. Each one is 4 bytes long, so this computes the address one past the last byte of the array. So this basically tells us this is one past where the array ends. We'll see how that's used later. Remember, let's say we have two things in the arrays. Let's say 17 and 21. This is what they'll look like in hexadecimal in memory. 17 is 11. It's a 4-byte 11. The low order bits are here because of little endian and 0, 0, 0. 21 is hex 15, right? 16 plus 5. And there it is. Okay. And so at the end of this, RDI is going to hold the value 2 because there were two things in here. And RSI is going to point right here. Initially, it pointed right here. Sorry, RSI is going to point here. RCX, pardon me, is going to point right here at the first byte past that. At that little gray box. So then what we're going to do is we're going to go ahead and get the 4-byte, the D word, pointed to by RSI and put it in EDX, which is the 32-bit register. So this goes and gets the 0th element out of the array and puts it in EDX. I compare that to the maximum, and then I do this thing, this C move B. What is that? That is a conditional move. There's a whole family of those, and C move B is conditional move below. So if our current maximum is below the thing we got from the array, then we want to make our maximum into the thing we got from the array. So we do this move of EDX into EAX, but only when EAX was below EDX. And that's great, right? We had a branch in our code. We had a compare and a branch, but they've replaced that with this single instruction that does this only when certain flags are set. That saves us from some branching logic and makes our pipelines continue to fill up and the program overall run faster. It's an important optimization. We could do that. We could replace this in our code. We'd save 1 byte because the instruction is longer, but we'd eliminate a branch inside our code, and that's worth doing. Okay, so next, we go ahead and add 4 to RSI. So RSI initially pointed to the first entry in the array. Adding 4 to it means it now points to the next entry in the array. So we're not using an index variable. We're just advancing the pointer itself. How do we know when we're done? Well, we check to see if we've hit RCX. Remember, RCX was the first address past our array. So once we hit that, once those two are equal, we want to stop. So while they're not equal, we'll go back up here to 10. And once we're done, we return with our current value in RAX. And there we go. And if you're curious about this jump not equal 10 being turned into 75F0, here's how that works. The RIP value currently points here at 20, and then you can just count backwards. F, E, D, C, B, A, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So here's F0. Look at that. We're at location 10. Okay, or you can do the math. The math is shown over here, right? We take this, we subtract that, and we get that. Pretty straightforward stuff, right? All right. Let's make some improvements. So one of the things that we learned from looking at their code is that we can do this conditional move. So we can replace our older code with this, which has a conditional move in it. And that's great. That saves us from that branching logic and having to have that additional label, and that's good. In addition, they took the contents of memory and put it in a register and then worked with that. Let's do that too, right? We had 2 memory references in the body of our loop. Now we just have 1. So we go get the contents, put it in EDX, we do the compare, and then maybe we move that into EAX. So now there's just 1 memory reference as opposed to 2, and we've eliminated a branch by using CMoveB. That seems great. Now, this is all looking pretty good. What about one additional optimization? That would be to use the loop instruction. So there is a family of instructions which are loop, and there are several of them, and I'm not going to go through all of them. It's an ugly family. Loop is the pretty child in the otherwise ugly family, and so we're going to use it. Here's how loop works. When the loop instruction is encountered, RCX, the count register, is decremented, and if the result is not 0, then it takes a branch. And in this case, it would go up to the branch labeled target. If RCX does hit 0 after being decremented, then it falls through to the next instruction. And no flags get set by any of this. Okay, so let's take a look over here at this code. We set ECX to 20. We zero out EDI. Here's the top of our loop. Each time in our loop, we increment EDI, and then I do a loop to top. So ECX starts out at 20, which is really 20 because it's not hex. And we'd come in here, we'd increment this by 1, we'd loop here. That decrements ECX, so now it's 19. It's not 0, so go back to the top. When eventually it hits 1, we decrement it and we'd fall through. So it will do this with it'll go through this with every value of ECX from 20 down to 1, but not 0. It will never be 0 in this loop. And then we'll terminate, okay? And so this code has the exit value 0. Oh, sorry, exit value 20. And here is basically what that looks like. Here's some C code. C is the start value. Then I do a do while, decrementing C each time. That's basically the same as the code you have over here. So we can use loop in our program, and because there's a trick here. I can use RCX as the index into the array. Does it matter when I'm finding the maximum if I start from the back of the array or the front of the array? No, it doesn't matter, which means I could run the index backward, and that's what I'll do here. So I will take EDI, the number of things in my array, and I'll put it in ECX, the count register. Then inside the body, I will take the base, RSI, I'll add RCX times 4, and I'll subtract 4? Why am I doing that? Well, if I had 2 things in the array, initially ECX is 2, and then next time through it's 1, and then we terminate. So it never is 0. So I'm always off by 1. So I want to subtract 1. What I'd really like to do is say RSI plus RCX minus 1 times 4, but I can't do that. So I subtract 4, which is the same thing, right? Just do the distribution of the multiplication. So this moves me back 1 so that now I'm looking at at each one of these, including the 0th one. So I'll do that, move that into EDX, and then here at the bottom, I just do loop to dot loop, and that's it. I'm down to just these few instructions. I'm able to do that because I've learned that I could run it backwards, something the compiler didn't know, and there you go. I can maybe make things a little more obvious in terms of this by declaring a macro. So up here, I've declared a macro. I do this basically the same way I do it in C for simple one-line macros. Longer macros are more complicated beasts in NASM. But where I would have a pound define in C, I have a percent define, and that has the same effect. Here I give it a name and I put an argument in parentheses, and here I give it the expansion. And just like with C, it's good and defensive to put the result in parentheses over here, so I don't accidentally capture a name I don't want. So this looks identical to how I would do a pound define, and it works the same way. So down here, this gets expanded, RCX gets substituted for B inside here, and I get this result. What's the point of all this? Well, there are a lot of instructions. Some have specific cases. An ordinary algorithm can start out pretty obvious and then rapidly become difficult to understand. And it's easy along the way to make some hard to find errors. Don't necessarily start out trying to write optimized assembly. Write obvious assembly, and then you can optimize it as you go forward. The other thing to note is writing assembly will still often beat the compiler because you may have information the compiler doesn't. Okay? If you really want to obfuscate a program, convoluted assembly is a great way to do it. Here are 2 programs. This is the initial one we wrote to find the max of the list of integers. Here's the one we ended up with. So you should take a look at this, read through it, be sure you really understand what's going on in here, and just remember, this was sort of the obvious way to do it. This was the maybe less obvious way, but significantly faster. We really beat the C code with this. There are a lot of assembly instructions, documented and undocumented, some for specific cases, and you can learn a lot by seeing what a compiler generates. And the easiest way to create an assembly program is to write it in a high-level language and use a compiler. That's still the easiest way to do it. But there are some things you can only do in assembly, and you can sometimes still beat the compiler. Sometimes. Compilers are pretty smart. A lot of smart people building them, but sometimes you can get ahead of them. Let's talk about the ELF format. So I've mentioned executable files a few times now. They contain the information necessary for the operating system to run your program. And there are many different formats. The most common are the portable executable, a PE file on Windows, the Mach-O format on Mac OS, and the ELF format on Linux, Unix, Android, some others as well. Very common, widely used format. And there are others. You go to Wikipedia and you can see them all. A.out is an old file format. When you see an A.out file in your system, it's not an A.out format. It's actually an ELF. But the name is a holdover. So what does ELF look like? Well, we can look for the definition of ELF in the include file that defines the structure. We'll find that in user include ELF. It's in there. It's partially documented, and you could write code that used these data types if you wanted. But there's an explanation, but it's not necessarily super clear what everything is, right? So here we have object file version. Well, what is that? Entry point, program header, processor specific flags. What are those? The rest of the definition is found in the man page for ELF. So if you do man ELF, it's in section 5 of the man pages, and now you'll see a lot more information. So you really need the header file and the man page together to get a clear view of what's in the different versions of the ELF file. The ELF file format is what's used in Linux if you're running Linux on a Raspberry Pi, if you're running it on a supercomputer, if you're running on your desktop, it doesn't matter. It's the ELF format. It supports lots of different processors, lots of different instruction sets, but the basic structure of it is the same. There's a Hello World Elf tutorial you can go and visit and play with. There's something called PyElf Tools, which is a Python library for manipulating PE files. We're going to use that, but not right away. The other major formats, they really basically have the same information in it, but in a different structure. In fact, because it's basically the same information in a different structure, there's a tool called objconv, and there's a link to objconv right there, that will translate one format into another, and it mostly works. These guys right here, these are giant posters of the format of these 3 different file formats, and you can click through to them and go have a look at them. Most modern operating systems do things effectively the same way, differences in the conventions that are being used. So if you learn one, you may be surprised at how much of that translates over to the others. Let's talk about some tools, specifically objdump. We'll go back to objdump for a minute. Remember, we got objdump from binutils. I've used a few of these little options here, but here's some common ones. F gives you the file headers. H gives you the section headers. So over here, we see the section headers for a file, right? And there's .text, our friend .text that contains our code. You can see that in addition, some other things may contain code as well. Interesting stuff over here. .x gives you all the headers. -t gives you the symbol table, and -r gives you the relocations. In addition, there's a tool specifically for ELF, right? Objdump is not specific to ELF. Objdump tries to understand lots of different things. And it uses something called the binary file descriptor library. But readelf is specific to ELF. And so it'll give you the same information, but sometimes it gives it to you in a slightly different way. Sometimes it gives you a little more information because it is specific to ELF. Here are the same things, same options. H is the file headers, capital S is section, E is all, S is symbol table, and R is relocations. So there you go. One thing you can do is say readelf-D to see the libraries that are dynamically linked. If you're on Solaris, you don't necessarily have readelf, but you have elfdump, and you can use it in much the same way. In fact, it's got some interesting features to it. Symbols. So readelf-S or objdump-T will show you the symbol table. So these are all the symbols that are defined in your program. And they include the obvious ones like _start and main. And then they include some other things like things you might have defined in the course of your program, like message might be the location of a simple message in your code, etc. Some of these can be just values that are computed and put in here, like text len, the length of a piece of text, etc. There's a video called Tables. It's up in iLearn, and it covers this in a lot more detail and uses XXD to probe them and look at what's in them. Let's talk about sections and segments. A section in a program is just a linear sequence of stuff that has the same access rules. It's executable, or it's not executable, or it's writable, or it's not writable, so on. A segment is a section of contiguous bytes loaded into memory and given specific rules. So sections you declare when you declare your assembly code. The linker sees that and it tries to lay them out into segments, which can then be allocated against pages and loaded into memory and have certain access rules associated with them. So segments are used during loading. Sections aren't. Sections are there for you, for the linker. Post-linker, the section table is not really used. It's still preserved, but really just the segment table is used. Okay? You can have, a section can be present in more than one segment, and we'll see that. And some other funny things can happen. Basically, a section is the smallest unit of an object file that can be relocated by the linker or moved around. So here's what that might look like. The text section might go in a segment that has read execute permission. Data and read-only data might go into a segment that just has read permission. We might have this read-write thing over here as the stack, because we need a stack. Stack has to have a segment. We didn't have a section for stack. That's okay. The linker knows to give us one. And because of the flag, it knows to give us one that is not executable. And we might have a section that doesn't go anywhere, just informational. Okay? We can take a look at all that with this little piece of code on the right-hand side. So we have some different sections defined here. We have not home, which we say we want to not allocate, and it contains 3 data bytes. So we don't want to allocate that, even though it has data bytes in it. We'll see how that gets handled. Here's an empty section. We just define a value inside that section, but all we're doing is giving a number associated with this symbol. Here's our program section, section text. And here's our data section. And notice how they play together. The program is going to return this retval in EAX. Where does it get retval? It gets it from here. Retval is a double word, a data double word equal to val. What is val? Val is set up here to be 22. Interesting. Let's see what the assembler makes of this. So we assemble it, and now we look at the sections with -H and the -W flag to make it wide. And we see all of these. Here's not home, which in fact contains 3 bytes, and it occurs at offset 2C0. It is read-only, but you notice I said no alloc. It doesn't have the alloc flag that everything else has. So it's not going to get allocated. Here's empty. Empty has size 0. There are no bytes making up empty. It's at 2D0. Since there are no bytes, you'll see the next section starts at the same location. And it has alloc and some other flags in here. Here's text. Text contains code, so it's executable. It's read-only. Again, writable or executable, but never both. It starts at 2D0, and it contains 7 bytes. Here's our data. It contains 4 bytes, and it's just data. And you'll notice that we've aligned these so they sometimes don't start right at the end of the next one. And then finally, here's our stack note, which has size 0, and there you go. Once we link, once we've assembled, post-assembly, pre-link, looking at this with readelf shows us the same thing we saw before, these top 5. It additionally shows us this weird null at the top. That's just an artifact. It's just going to show us that. Nothing important about that. You might see why that occurs if you watch the little video on the tables. But it also shows us these 4. Now, objdump didn't show us these 4. It just chose not to. And these are the shared string table, the symbol table, the string table, and the relocation stuff. Now, these three tables are covered in the video. Okay, I'll explain what's going on in those. This has to do with relocations. We will spend a lot of time discussing those later on. So now we've linked. And so let's look at our section table post-linking. And we'll see that now there are 30 sections. Holy cow, that's gone crazy. And we see something has changed. So here are our sections, .text, .data, .nothome, .empty is gone. Because .empty was empty. We discarded it. It's gone. Not home is still here, right here, even though it's not allocated, right? The A flag is present for a lot of these to indicate they should be allocated. It's not present here. And there it is. Even though its size is not 0, we haven't asked for it to be allocated. What about our stack note? It's gone. It's not here. It was empty, just like our empty one was. So it's been discarded as well. Is that okay? Well, if we go and look at the sections with -L in readelf, we'll see that here are the sections, and we'll see that there is a stack, GNU stack, right down here, and it's readable and writable and not executable. No E here. So that's already been taken care of. That little note has had its effect of making sure our stack is not executable. So we don't need it anymore. We can look at the section to segment mapping. This is shown right after the segment table. Here we have the segments numbered. Conveniently, it does not number them here, so we have to count them. So we find interpreter is in section 1 and 2, and we find dynamic is in 5 and 6. 5 and 6, well, right, so it's we got to count now, and we'd find out that, yeah, sure, here it's in these. So let's pull that out. It's worth noting that not home is not mapped to any segment. Therefore, it won't be loaded at runtime. That's okay. We said we didn't want it allocated. Notice it wasn't empty, but it never made it into memory. So we can put stuff in the binary that does not get loaded. Here's .dynamic. We see it has a VMA of 300 and the links of 1C0. And we can ask how that relates. So here we have it, 3E00, size is 1C0. That's our .dynamic section. Section 5 is given here. It has a VMA of 3DF0, which is a little before that, and a length of 228. And so it's going to end at 3DF0 plus 228, or 4018. So it runs from 3DF0 to 4018, and that contains this. That contains all of, so dynamic is entirely contained in segment 5. How about segment 6? Segment 6 runs from 3E00, that's the same as this, with the length of 1C0, that's the same as this, and so it ends there. It completely is overlapped by section 5. So segment 6 is completely contained in segment 5. They're not distinct. That's interesting. So dynamic is really loaded just once, but it can be found using this little segment table. Those are exactly the same. If you want to understand it, go read that stuff there, but I'm telling you the linker is a nasty piece of business. The reserved system names, I'll start with a period. So if you're going to create your own section names, don't start them with a period. That way you won't accidentally run into a reserved system name. The VMA and the LMA, the VMA is where the segment should be loaded. Of course, that is almost true, but not quite because of address space layout randomization. And the LMA is usually only different when you're doing something with something like a ROM. That's it.